Welcome to Ruby Thursday. I'm Melissa Wanish. This is a recording of the Ruby Roundtable meetup, which happened in New York City on September 20th, 2017. Thanks again to our sponsors ThoughtWorks for providing space and Flashpoint for providing food. At this meetup, David Kurutz took us through developing a peer-to-peer network with his team. Enjoy this recording of the Ruby Roundtable.
Thank you all for coming. My name is David. I'm a software developer in Brooklyn, New York. And today I'm going to be talking about really kind of the journey and the problem space that me and my team encountered as we set out to build a peer-to-peer file sharing application from scratch. So, quick little agenda of what we're going to be touching upon. We're going to look at the problem set, peer-to-peer space, and the key features that we sought to implement. We're going to look at distributed hash tables. What are they? Why are they? What do they do? File sharding and retrieval. Not every peer-to-peer system does that, but BitTorrent does, and so does ours. The overall development strategy that we took, and the final system architecture.
Can I interrupt real quick?
Of course.
What was the goal? Like, was it personal, for profit, or for fun?
Good question. Personal, educational, for fun.
Cool.
By no means did we attempt to replace BitTorrent or even think that we're contributing something particularly new to the space, as much as it was wanted a big project, wanted to not just build another Rails app, some sort of outside of the box project, right? What is Zorro B2B? The tagline we're working with is it's a BitTorrent-like peer-to-peer file sharing application built from scratch in Ruby and Sinatra. Experimental working proof of concept software, and it's so BitTorrent-like. Like, why BitTorrent-like? In our system, you add a file to the network. It's broken up into pieces. Those pieces are documented in a manifest file, like a torrent file. If you have a torrent file, you can look at it, iterate over the list of pieces, look out onto the network, grab all of them, put them all back together, you have your file. So that was the model that we're looking at. So there's a bunch of engineering problems, right? How does a node, like an instance of this software, keep track of other peers, right? There has to be some sort of way for us to discover other peers. There has to be some sort of way for us to keep track of them. Where are they? Where are they on the LAN, on the WAN? Where are they? We need to be able to communicate with them. And we need to implement some sort of remote procedure called language that they can set, so such that they can send messages to each other or respond to those messages. A node's going to need to know about the files that it has, and it needs to broadcast those files to probably not everyone, because that could potentially be a lot, but it needs to broadcast it to the most appropriate nodes that should know about these files. And we need to be able to find the peers that host a file. The whole point is you have this manifest file, you want to give me this file. I'm looking up where is this file, deliver it to me. What's the most appropriate place? Who knows where it is? So as it turns out, distributed hash tables actually solve a lot of these problems, and we're going to dive into that a little bit. Some other engineering problems we have to deal with were like file sharding. Like, how do you chop up a file into little bits? That's actually, in the beginning I thought that was a really difficult problem, but it turns out to be one of the more simpler pieces. Once you chop up the file into little pieces, how do you keep track of them? We're going to document them in a manifest file. How do we retrieve them? How do we reassemble them? Aside from just the engineering problems, there was kind of like a development strategy problem for a number of them as well. How do you scale the development of a network application? We could write classes and objects and tests and fire up IRB and get objects communicate with each other. But that's a little bit different than, say, doing it between my laptop and my Mac Mini, or doing it between my Mac laptop and my friend's laptop in San Francisco. So architecting a system that scales from a local environment to a full-fledged WAN environment. We also need to be able to allow our application to be instantiated in bulk. So a peer-to-peer application really isn't worth much if there aren't any peers. So if I'm working on my laptop and trying to build this thing, I can't just boot up one instance of Sinatra. So I need 40 of them in order to actually see that it works, right? So building a system that we can launch multiple nodes in any given environment. Furthermore, I think the largest problem we faced was how to quickly internalize a new vocabulary and communicate with each other. Here's the team. The team's Terry Lee in San Jose, Ken Chen in Taipei, Taiwan, and there's me in Brooklyn. We worked together with lots of pair and trio programming throughout the summer. I think the hardest part was internalizing this new language. What are these concepts? What do they do? And now we need to describe them and mutually agree upon an understanding of what these things are, while crossing not only time zones and areas, but also a language barrier of, Ken not a native English speaker, so there was so much time spent just communicating these basic ideas back and forth, so we had a really good grasp of what is a distributed hash table, how does it work, what do the internals really do, and that proved to be really important in all of our collective understanding of what to do here. So before I dig too much deeper, what I want to do is kind of just show you what we did and show you how it works, right? So pardon me here and all of the screens. I'm going to fire up a node on my local machine. So here's the web UI that we built. And that's not really the important part, but here's the web UI. Were we hosting any files? We'd see them here. We can enter an ID, retrieve a file from the network, drag and drop, upload a file. There's a debug menu that shows us the routing table. Here's some other, here's nodes that our node's aware of. Let's just so you can see what happens when we retrieve a file, right? Here's my data store. This is just the sandbox that my node's operating in, right here, Finder on the right. So I happen to know the ID of a node that's hosted on the network. File IDs are the SHA-1 hash of their content. So that's an ID that I just know is there. So I'm gonna hit submit, let's watch what happens. So first we grab that manifest file. It's iterating through the manifest file, grabbing all the shards, and finally it assembles the shard and places it in files in the files directory. We can then watch it here, or we can just click on it and go to watch it through the web UI. That's more or less what the software does. We can also share a file onto the network via drag and drop. Because I don't know what's going on with the network here, so I don't know if I want to demo that part of it. It's kind of high risk. All right, so moving onward. All right, we're back. So I mentioned that distributed hash tables kind of solved a lot of problems that we faced here, as far as how do we find where anything is located in this variable world where we don't know really what exists out there. So what's a distributed hash table? Well, I think maybe we should take a step back. We all know what a hash table is, right? It's a set of key value pairs. It offers O of 1 time complexity for lookup of a key, insertion, deletion. It's a very efficient data structure. Now, it's not entirely obvious to the user, but what's actually happening is behind the scenes we have an array. And the key actually somehow maps to an array index, and that's actually where we're storing something. The hash table is like an abstraction on top of that. So how does that happen? Well, there's a hash function. So, for example, we take a key, we run it through a hash function, it produces some integer. We then calculate the modulus of that integer with the length of the array that we're storing something in, and we get a number, an integer, that represents an index of the array between 0 and the length of the array. Provided that the hash function doesn't change, and provided that the array does not grow or shrink, one input will always produce the same output. We can always find an index to insert a key. Now, obviously, there's a little more to it than that, right? Like, what about hash collisions? What about array resizing? Yes, that also happens, but not really so important to what we're talking about right now. A distributed hash table is not unlike a regular hash table. Instead of running our key through a hash function and having that dictate which array index we insert into, it's actually going to dictate which network node we choose to store a value at. Same principle, it's just not an array anymore. Now we're just shooting it out to a particular network node. Now there's a number of ways to do this, right? A lot of very smart people have written some very fun to read white papers about how to do this. Cord, Pastry, Kademlia are all a number of ways that this can be implemented. We chose Kademlia to run with. Why? That's what BitTorrent uses. It's quite prevalent. It has 4 remote procedure calls, so that was kind of nice to think that we only had to think about like 4 endpoints that we're sending requests to. Yeah, that was really the reason. So we're going to dive in and take a look at Kademlia a little bit. So the Kademlia specification defines the structure and behavior of a distributed hash table. So we have a network. The network consists of nodes. A node is an instance of software running on one particular host. Each node has an ID. That ID in Kademlia is a 160-bit integer. Now, 160-bit integers are kind of hard to think about. It's a really large number. So for a lot of this, we're going to be talking about 4-bit integers, just to make things a little simpler. Each node also has a routing table. It's like your contact book. The routing table contains contact information for every node that the current node comes in contact with. You'll notice that it's divided into buckets. Each bucket contains contact information for nodes of a specific distance to the current node. So there's this concept of distance, like a node logically can differentiate saying that this node is logically further from me than this one, not geographically, but logically. Furthermore, each node has its own segment of the distributed hash table. This is the hash table. This is like, you create a hash. We're storing key value pairs. This is where a node keeps track of that. Now, in the case of Zorro, what's a key and what's a value? A key is a hash of a file that we are storing onto the network, or telling the network is accessible. The value is a URL to that file. So here's the file's hash, that's the key. The value is, it's located over here. It's located on that node, whatever that IP address is, and that port and that path. Nodes communicate with each other. Each node has 4 remote procedure calls that we had to implement. So the first of which is ping. So ping, it's a lot like in IMPC ping, where you are checking to see if another node is alive, right? So node A says, hey, node B, are you there? Are you alive? Are you running? Are you on the internet? Sending along contact information. Node B is alive, receives the contact information, inserts node A's contact information into its own routing table, replies to the ping, node A receives the reply and says, great, I'm going to store this contact info. So they have a mechanism for seeing, like, are you there? The next remote procedure call we implemented was find node. The name's a little misleading. It's really more like find closest to nodes. So we have an ID. We want to say, hey, I'm node A. Hey, node B, where's this ID? Do you know? And it says, well, I don't know. But here's some contacts that are closer. So it starts to feel a little bit like LinkedIn, or a little bit like 6 Degrees of Kevin Bacon, right? Where I don't know how to get to this, but you look like you might be closer to it, so I'm going to ask you, and I bet you could probably at least put me in the right direction. So we're implementing these methods on these objects. All right, find value. Similar to find node, right? Find value is, I want to find this file. This file's hash is this integer. Where is it? You look like you know. If node B knows, it looks it up. Yeah, it has it. It replies with the location. At which point node A can issue another HTTP request and grab the file. If it doesn't know, though, let's say node A asks node B and it doesn't know, it rolls back to find node and it passes on contacts that are closer to the file ID that it's looking for. So still we have all these ideas of closeness, and determining closeness, you ask a node that you think is closer with the hopes that they will have better information than you have. The last remote procedure call that we read up on and implemented was storing. This is just setting a key value pair in the distributed hash table. So you have a file, you hash the file, and you have a location for it. Where do you store it? There's a million nodes on the network. Which one, or ones, is the one that needs to know about this key value pair? Well, you store this key value pair at the nodes whose IDs are the closest, there's that concept again, closeness, to the file ID. So how do we find nodes and files? It's just another quick, it's helpful to kind of humanize this a bit. We have these RPCs that we implemented. However, there's this larger piece in place. So once again, 6 Degrees of Kevin Bacon. I want to find the actor Kevin Bacon, and here's who I know. Here's who I know about. Well, probably want to ask the people who are in the entertainment industry, so I'm going to ask the person, Susan, who's in film, and Cameron, who's an actor. Susan knows Sarah Jessica Parker, who was in Footloose with Kevin Bacon, and Cameron knows John Malkovich, who was in Wings Logic with Kevin Bacon. So you retrieve that information, say, great, query those two directly, and hopefully, in the end, you actually go through enough contacts that you either reach Kevin Bacon's address, or B, maybe there's some sort of failure condition at which point you've asked all the people you can. You aren't getting any closer. Fine, I'm never going to be friends with Kevin Bacon.
It's probably for the best.
It's probably for the best, yeah. But you gotta keep trying. So, closeness. How do we calculate closeness? In a Kademlia network, closeness and distance is the bitwise exclusive OR, the XOR of two IDs.
I see what you did.
Everyone would like to get out their calculators. What does this mean? Just maybe some of us are familiar with this, some of us maybe aren't. Let's take the number 11. Supposing we're working in a 4-bit space here. We only have IDs 0 through 15 possible. It's a very small peer-to-peer network. I'm node 11. The binary representation of my ID is 1011. 4 bits. So that's not what I wanted. There we go. So what about, what if I want to find a file with the ID 10? Well, we can calculate the XOR of 11 and 10 by calculating the XOR of each digit of each bit place in the binary representation of the number from left to right. So if the two inputs are the same, we result in 0. If the two inputs are different, we result in a 1. So the first 3 digits are the same. The last one's different. 11 XOR 10 is 1. Does that make sense? Good. Take another example. 11 and 12. Here, the first digit is the same, right? So we get a 0. All the rest of them are different, though, so we get a series of 1s. 11 XOR 12 is 7. So this distance way of measuring distance is a little different than like Euclidean distance, right? Like saying that 1 and 2 are 1, there's a distance of 1. 2 and 3 have a distance of 1. Then we have all this overlap. There's many numbers that have distance of 1 from each other. When you're using XOR as your distance metric, it's always going to be unique. 11 XOR 10 is different from 11 XOR 12, even though they are only 1 apart in conventional Euclidean mathematics. Another example, 11 and 4, we can see first one not the same, none of them are the same. They result in a bunch of 1s. The distance is 15, it couldn't be any further away. That's as far away as it could possibly get in a 4-bit key space, right? So the XOR distance, the smaller decimal value you get, the closer the distance. If we look at this like as a binary tree, or really as a like a prefix tree, we can see that we'd have like an O log n lookup time, right? Because every left-bound child adds a 0, every right-bound child adds a 1. So we can get to any node in here with O log n lookup. There's another kind of like, there's another point here that's similar but not entirely obvious. Pardon me if we're getting a little heady. Shared bit prefix. So we're looking at this same chart we just looked at. So 11 and 10, XOR is 1, right? But more importantly, the first 3 digits are the same of their binary representations. So they have 3 digits in common. 11 and 12 have 1 digit of their prefix in common. It isn't until right here that they start being different. 11 and 4 are different throughout, thus 1s across the board. So this number here, the XOR distance, important, but more important is this number, the number of digits they have in common at the left to right prefix. That's how we track how close a node is. Going back to our binary tree. Let's say we're node 11, right? This entire half over here in green, those all get categorized into the same bucket. They couldn't be any further away from us. We have to go all the way to the top of the tree to find them. They have 0 shared bits with our ID.
Going through Williamsburg to get to Manhattan.
Exactly. Also, to note, there's a 50% chance, like 50% of all possible nodes will end up in this furthest bucket. Furthermore, if we take a look here, just who has 1 digit in common with us? Well, these 4 do. So 1 shared bit, we have 25% chance that those nodes will have something in common, a bit in common. Keep going, we can see 2 digits in common, and finally 1 digit in common. Going back to like the architecture of the Kademlia node, we have these buckets. Each of these buckets represents a shared bit length. So we discover all these nodes. The nodes whose IDs have nothing in common with our own, they go in 1 bucket. But that's 50%. That's like half of the things we're going to encounter. And it's also those are the least important ones because they're so far away. So we don't keep track of those. We only hold on to 8 of them. The nodes that have 1 digit in common with us, we keep them in another bucket. And furthermore on down the line. In a 160-bit key space, we can hold on to 160 different buckets. If a node wants to store a file or look up a file, it looks at the hash of the file, calculates the distance between its own ID and the file's ID, then says, all right, I have 3 bits in common with this ID, so that this file should be stored at the nodes that I have 3 bits in common with. If I need to look it up, I look it up at those nodes. So, any questions? We're going to move on to another section outside of Kademlia. There's really a lot more to it than that. That's kind of a nice overview. If you care to learn more, there's a bunch of research, but to be quite honest, going deeper into more inner workings of Kademlia would require a couple more presentations. So we're going to move on to file sharding. So what is file sharding? Chopping up a file into little pieces, right? But we can't just chop it up. We have to maybe name them. We have to document them. We have to associate them with the file that they comprised, make them retrievable, advertise them onto the network. So that's essentially what we did, right? When you drag and drop a file into a Zora node, the file gets broken up into 1 megabyte pieces. That 1 megabyte, that's arbitrary, it could be anything, but we chose 1 megabyte just really arbitrarily. Each of these files needs a name. What do you name it? Well, we're going to retrieve it by its hash. So the name of the file is the SHA-1 hash of the file's content. Then those files are documented in a manifest file. The manifest file's name is the SHA-1 hash of the original file's content. So way of saying looks kind of like this. Let's say that this here is the hash of our file name. Document an XRO file, and we document the file name, the file length, and then we have an array of hashes. So earlier when I demoed that, I demoed the system, I put in the hash of a file. We did a lookup for that file's hash, found the manifest that holds all or documented all of the shards. We retrieved that manifest, then iterated over this list of pieces, the shards, retrieved each of those from whichever source appropriately was hosting them. Once we had all of them, we stitched them back together and named that file the name that's documented in the manifest. The last kind of point that we want to, well, two more small sections here. The 3 of us on the team had a variety of different backgrounds within development. I was really the one who had a background in systems administration and IT kind of things. So the thing that I found really most interesting about this project was the development strategy. How do we get from I'm writing classes in Ruby, and instantiating them, and telling them to talk to each other. How do we get from that to talking over the internet? In the beginning, like as I said, we had classes and test suites. They're reading research papers and translating the specs into code and testing that it behaved the way we hoped that it did.
Or worse ways to start. There are worse ways to start.
Right? Yeah. Right? There was no network, there was no communication. It was, we're firing up IRB and saying, hey, you're an object, execute methods on each other, go. And then putting that in tests and scripting it. We're even working with mobile computers. So we have all these functioning tests, how do we get from tests to, what would be the next step? Maybe the ability to have 20 or 30 nodes on my computer, no network yet, right? But 20, 30 nodes on my computer, at least communicating with each other via HTTP, right? How do we get to there? Because that's the logical step before we actually implement a real network, multiple computers, firewall rules. So the solution was to delegate all network communications to a network adapter object. Now, in the case of tests, this is really just kind of a fake network. It's really, we need a way for an object to tell another object, hey, find another object for me, deliver it this method, call this method on it. So really it was just kind of like a shell wrapped around an array full of other nodes. So let's just take a look at how to ping work, right? So node A wants to ping node B, just tells the network to do it, right? The network looks in its array to see if node B even exists. Sure, it does. So it calls a ping method directly on node B, receives some sort of reply, right? Or some sort of really a return value, and passes that back to node A, which is happy to know that it has a friend. And here's some of the code that here's kind of edited code of what this looked like. We have part of our node class, and on the right we have part of our network adapter class. We can see that our RPCs are passed off to the fake network adapter, which locates the receiving object and executes some sort of receiving RPC method on it. Now, so what are we getting at? We're getting at actual network communications. So we don't want our tests to fail. We don't want to swap out some entirely different thing and have to build things up from scratch. So what we do in a real network, local sandbox with multiple nodes on one machine, is we swap it out for a real network adapter. Now, what is a real network adapter? Well, in our case, it was an object. It was a class that has the exact same API as the fake network, but instead of finding an object in memory and calling a method on it, what we're actually going to do is craft an HTTP post request, send it to the Sinatra endpoint that node B is presenting to the world. We get an HTTP response, passes it back to the network object, and now we essentially are proxying these method calls through HTTP. And here's what some of that code looks like. If you notice on the left, the node, it's all the same here, right? It's just making a call to the network. But now we have this network adapter that's constructing an HTTP request and sending it to a Sinatra instance, to a route here, that in turn calls a method on the node on the other side. Well, I should have been clicking through a lot of that. The last step was deploying over the actual internet, right? So it's one thing to have network operations happening on localhost on my laptop. It's another thing to maybe have it happening between my laptop and my Mac Mini. But the minute we start getting the internet involved, things get a little complicated because unless you're going to open up firewall ports, start forwarding ports, or you're going to put your computer directly on the internet, your machine's not going to accept an incoming request. So in the real world, how is this actually solved? Well, there's turn servers and stun servers, and there's hole poking techniques. I think WebRTC also has, WebRTC has some methods for direct browser-to-browser peer-to-peer communications. But in all honesty, within the scope of what we were trying to do and in the time frame we were trying to do it, this seemed like a problem that had already been solved by someone else, and we just kind of needed to get around it in a working system. So what we did was we, one, enabled support for third-party tunneling tools like ngrok, just so we could at least see it work over the real internet. And we built out such a way that our node could be instantiated flexibly with a number of different environment variables so that we could say, I'm going to launch 30 nodes in a test environment. I'm going to launch 40 nodes all hosted on Google Cloud. They all have public IP addresses. There's no firewall. I'm going to launch a bunch of nodes that know they're behind a firewall, but this port is forwarded. Essentially, built out, here's what the class looks like. We have all these environment variables and these conditionals such that if this environment variable is set, our node is self-aware enough to behave a certain way and broadcast itself to the world knowing certain things. What are some of these things? Well, like what's the HTTP port? What's the IP? Is there a fully qualified domain name? Is it a leech? Like if you're behind a firewall, maybe we just don't even want to deal with broadcasting, data like that you're offering up files to the world. Number of other variables that we set up.
Sounds like you've built a whole configuration management system for network nodes.
Kinda, yeah. That was I ended up being really kind of particular about that part of it because I was just like,
yep.
I don't want to build this system, and then like when someone asks, well, how did you deal with NAT translation? I'm just like, we didn't. Finally, I wrote a bunch of bash scripts such that we could easily roll out multiple configurations, just spin up an environment quickly. For example, we have like 30 or 40 nodes on Google Cloud, and didn't want to spend the money, so they're all hosted on one instance running on multiple ports. So how do I spin up 50 web servers running on ports 9,000 through 950, all that behave a certain way? You write a script that passes environment variables, and the classes are looking for them and instantiate things to behave that way. Finally, we reach the end. Our system architecture, our total full system architecture looks like this. We have the Zoro node, which is kind of encompasses the whole network application. There's a Kademlia node that really provides the routing, keeping track of contacts, and the keeping track of what data is stored. It's really the brains of the application. It has access to the file system through some file utilities. That's how sharding manifests. Sharding manifests and just tracking files are done. Furthermore, it communicates to other nodes via an HTTP gem, just to send outgoing HTTP requests. And there's a Sinatra web UI for the front end. Sinatra is also handling all of the incoming remote procedure call routes as well as file transport when you go to retrieve a shard.
Did you do anything with long-running request sessions?
I'm sorry, say that again?
Did you have to do anything with long-running requests through Sinatra, or any tweaking as far as the actual HTTP transactions?
You know something? We did not have to touch upon any of that. I bet long term we probably do have to touch on that, right? There's a lot left to be done, and I hope to be able to keep working on it. Specifically, HTTP really isn't the most efficient way to be building this out, but it allowed us to utilize pre-existing tooling, so we didn't have to reinvent the wheel.
Yeah.
The most difficult part of this was Kademlia, was implementing a distributed hash table that really took up more than half of the time of development, such that once we had the distributed hash table part working, everything else fell into place extremely quickly afterwards, as far as how do we shard a file, how do we get it, how do we put it back together.
It's amazing what you can do with the register and gears.
Yeah, really. So that's pretty much all I have to talk about. If you want to learn more about what we did, there is a GitHub pages available at that URL. I am also looking for work, so if anyone knows anyone who wants to give yours truly a job, or anything else I might be good at here, that's my contact info. Please feel free to reach out. And that's that. Does anyone have any questions? I'm sure we got a little heady here.
That's great.
No questions.
Do you feel satisfied? Do you think you've achieved your goal?
Yeah, I feel pretty good about this. Like, going into it, it was this very open-ended, like how far can I get? Like, it was kind of really an ambitious project.
Yeah.
And the fact that we have a working solution, you know, it's alpha, it needs some work.
Yeah.
But it works.
You can show it off.
Yeah, and I really learned a lot along the way. I think also, there's a difference between I remember the confidence boost that I got when I first built a thing, right? But then by following a tutorial, but then there's this, we just kind of were reading research papers.
You're designing.
Yeah, and that felt really good. Just kind of coming out on the other side of this, feel like I can kind of probably solve any problem.
Cool.
Yeah, really good times though.
All right.